Okay, we are at section 8.3, and I'm going to throw a little bit of 8.4 because 8.4 is really just one slide. So we're going to talk about situations involving kinetic friction. So this is the idea here. You push the book from actually the dark blue is the original position, and the VI, you end up at the shaded position. And notice that the velocity is to the right. The delta x is just a distance. The velocity comes to 0 because of the force of kinetic friction. Now, notice the force of kinetic friction is opposite the velocity. So basically, we modeled the friction as shown in the picture. The entire friction force is modeled to be applied at the interface between two identical teeth projecting from the book and the surface. This is very idealized, but it gets the idea across. The point of application of the friction force moves through a displacement of magnitude d divided by 2. And there's a lot of derivation going on here, and I'm not going to go through. You're welcome to go through it, but I think if you just follow the examples and the examples that I do for problems, we'll get it. I do want to get to this last slide where the work of the sum of the work of other forces plus the integral of the kinetic friction dotted with the dr equals delta k. If you remember the dot product, if you were to dot a and minus a, whenever there's 180 degrees, you're going to be minus. So the work of other forces is equal to minus the integral of fk dr. In other words, they're in opposite. F is one direction and dr is in the other direction. And if you do the dot product of that, it becomes minus. And that's why this integral becomes negative fkdr. So the work minus fkd equals delta k. So the change in kinetic energy plus the change in internal energy equals 0. And so that's minus fkd, the change in kinetic energy is minus, it's the force times the distance, but the force here is just the kinetic friction times the distance plus the internal energy equals 0. So the change in internal energy is equal to the friction force times the distance. So the work done on a system by forces other than friction are work equals delta K plus the internal energy. Okay, you're traveling along a freeway at 65 miles an hour. Your car has kinetic energy. You suddenly skid to a stop because of congestion and traffic. Where is the kinetic energy of the car your car once had? It is all internal energy in the road. It is all internal energy in the tires. Some of it has transformed to internal energy and some of it transferred away by mechanical waves. It is all transferred away from your car by various mechanisms. Well, we're going to pick C. In other words, the tires are warmer, the road is warmer, and there was probably screeching, so there was mechanical waves. So the C is the answer. Now, changes, we're going to continue on. There's only one slide for section 8.4, changes in mechanical energy. The same picture, the book is, you give it an initial push and it's sliding to a velocity of 0, velocity initial to velocity 0. If you recall previously, it was the change in kinetic energy plus the change in gravitational energy equals 0. Now they've added the internal energy. So that's the now we have to take into consideration the internal energy, and I do some homework examples to help you through that. Hopefully that'll be of use to you. And then the next section we're going to do is power. So why can't I see my cursor? There it is.